So I'm Pietro Foti, and I'm a postdoc at the La Sapienza University of Rome. And I'm here today to present you this work about the fatigue assessment of lattice structures through SED method. This is a work in collaboration with the University of Padua. And you can see here the outlines of these works. I will present you the aims of this work and then the experimental campaign that we have carried out in order to prove the aims of our research. And then after this, I will present you the SED method and its use in the case of lattice structures. After that, I will go to conclusion and further developments. But first of all, let's start with the aims. The aims of our research in this case was to investigate the fatigue behavior of stratum-based structures that, as you well know, is a type of components that is gaining a huge interest during recent years, both from the academia and industry. In order to prove this first point, we have carried out some original post-adaptive fatigue tests conducted in the high cycle fatigue regime. We have also done some XGT scans and carried out the failure analysis in order to identify the failure initiation point for this particular kind of component. After this first part and considering the outcomes of this part, we have considered which one could be a suitable fatigue assessment method in order to account for the geometrical complexity of these particular components. And considering the outcomes of the first part, we have concluded that maybe a local approach could be a valuable solution to investigate to foresee the fatigue life of these lattice structures. So here you can see the details about our experimental fatigue campaign. We have focused on the 316 stainless steel that we have produced considering these AM process parameters. And you can see that we have two types of, let's say, more common specimens. We have the smooth one and the sharp notched one that we have used both to relate our results to other data in literature and also to calibrate our local approach to foresee the fatigue life of the lattice structures that you can see on the right that are based on an octet class unit cell. And the tests have been done with a load ratio of 0. Here you can see the results of our experimental campaign, and in particular you can see on the top of we have reported the results in terms of nominal stress, but I would like to stress out that the first one on the top, so the results related to the smooth specimen and the notched specimen, are related to the net cross-section, while being more difficult to determine net cross-section in the case of the lattice structure, we have reported the results for this last specimen in terms of load over the gross cross-section. After this, we have carried out some fatigue failure analysis. Here you can see a detail for one of the specimens that we have studied. In particular, we have gone to analyze each of the struts and try to understand where the fatigue failure started and how the other struts continued to failure after the first one. As you can see, we have identified that the fatigue failure started from the node that we have named B in this case, and you can see better in this slide that the failure started from the notch and propagates to the outer surface of the component. So, and regardless of the large presence of pores that you can notice in this STM figure, the failure started the notches. This conclusion, to be honest, could be foreseen somehow in also other works in literature in an indirect way. Because if you consider other lattice structure in literature, for example, the gyroid one, that, as you may know, is characterized by having not so sharp notches, in its structure, you can see that if we look at the effect of some surface treatment on this component, we notice an improvement if we manage to improve the surface roughness on this component. While if we look at some strat-based lattice structures, the effect of surface treatment is not so evident. Of course, here I just reported 2 of the study in literature, but you can find a lot of these, and more or less the effect of surface treatment is much more evident on gyroid structure with respect to the strata-based one. And this would mean that the strata-based one is essentially dominated by the notch effect at the nodes between the different strats. So, having established that the notches play a critical role in the fatigue behavior of this kind of component, we have thought that maybe a local approach could be a suitable way in order to foresee the fatigue life of this component. And considering some advantages that I will present you later of the SED method, we have chosen this particular local approach to investigate the fatigue failure of this component. Some basic concept about this method, in particular, the strain energy density method is a local energy-based approach that is validated during the last 25 years for investigating fracture in static condition and fatigue failure. And the very basic idea of this component is very simple. We have that the method assumes that brittle failures happen when the local aggregate strain energy density in a given control norm reaches a critical value. And the method is also extended to foresee the fatigue failure of components by relying on 2 hypotheses that are essentially that the fatigue failure happens in the inelastic regimes, and it usually shown a brittle failure. Another important thing that we need to say about this method is that the critical value of the strain energy density, both in static and in fatigue condition, can be assumed to be independent on the notch leveling angle, the loading condition, and the local geometry. So, as a matter of fact, this critical value of the strain energy density is a material property. But we have talked, I have said that the strain energy density needs to be evaluated in a control volume, but there are some clarification to be done about this control volume, and it has some particular features that need to be taken into account. We have that the control volume shape depends on the local geometry, as you can see here. I will not go so much into the detail, but what I would like to underline is, in particular, the control volume characteristic length, that R0, that is depending on the material properties and on the loading condition. And it is, as a matter of fact, a material property. An important advantage even by this method that pushed us to choose it to investigate the lattice structure is that it shows a very low sensitivity to the mesh refinement. So it is very well. It is very useful to be used with very complex geometries, such as the one of the lattice structures. And here you can see some mesh specification that allow us to use the method with a very coarse mesh, but still providing you some reliable results in terms of error in the estimation of the SED values. In order to apply the method, we also relied on some fatigue data taken from literature. This is because we have used the smooth specimen that we have tested as a way to relate to other data in literature that we can use it for our calibration. And in particular, we have found that the data from this work that were showing a failure starting from the microstructure was agreeing very well with our results, as you can see in the graph from on the right. And since the application of the SED method in the case of smooth components or more in details, in the case of components that do not present stress gradients, is independent of on the value of R0. It means that the curve that we have in this graph would provide us a curve in terms of cyclic average strain energy density versus number of cycles that is independent of R0. So we already know which is our fatigue curve, and now we only need to determine the value of R0 to properly calibrate our method. To do so, we have considered the sharp notches that I have presented in the first slide, in the one of the first slide, and you can see here that the R0 value that allowed us to consider other geometrical condition through the SED method has been found to be around 40 micrometer. And we have done this by minimizing the scatter index of the fatigue curve that is expressed here in terms of cyclic average strain energy density. But we also carried out a further validation of this value of the R0 that we have evaluated according to the classic SED method calibration, because the value apparently was a bit too low according to our experience. To give you an example, dealing with welded joints that are one of the most studied components through this method, the value of R0 is around 0.28 millimeters, so 40 microns appeared to be a bit low. But as a matter of fact, if we have looked into literature to find some value for the stress intensity factor threshold, and considering also the value of the fatigue strength at 2 million cycles determined through our test, we have found out that the R0 value should be between 27 microns and 61 microns. So apparently the value, even if it is low, it is a good estimation for this kind of material. Here you can see finally the validation of the method that we have carried out considering the real geometry for the lattice structure that we have acquired through some XTT scan. In particular, we have carried out a simulation using first a global model with the mesh size of 30 microns, and then we have focused just on the one most critical notch, for which we have done a sub-model with the mesh size of 5 microns. And as you can notice here, the value of the experimental specimen tested under the fatigue condition is well predicted by the SED method, by the fatigue curve in terms of cyclic average SED method that we have determined through our calibration. As you can see here, we have used just one real geometry to consider all the specimens, and this may also justify the slight this point at the very high cycle fatigue that are falling below the fatigue curve. Probably in that case, the local geometry was a bit different from the one that we have actually considered. But we also want to highlight that the scatter index for this band that we consider is also quite low, being 1.3, and considering a possibility of survival for the scatter band of 97.7 and 2.3. So at the end, we deemed our estimation quite good. Finally, you can see here a results for a summary of all the results in terms of the average density method, and at the end, the equivalent scatter index in terms of stress, it results to be 1.4. That is quite good, considering the probability of survival ratio that we are considering this work. So, at the end, to conclude, the key outcomes from this research was that we have further proved the leading role of notches at nodes in the case of strata-based lattice structures to consider their fatigue behavior, And we have also provided some results to prove that the SED method could represent a valuable solution to foresee the fatigue behavior of strata-based lattice components. As further developments, we are thinking to apply this method also to other lattice cells and different materials that may behave differently from this one, and in particular in a more ductile way. Thank you for your attention.